homework time, yes! Happy homework time is here again. Lesson 12, let's jump right in by writing our names at top of our papers. I'll write my name and you go ahead and write yours. And go ahead and write today's date. I'll write today, you write the actual date, where and when you are in this world of ours. Number 1. Instructions are circle the figures that have a correct line of symmetry drawn. I think you'll find symmetry pretty straightforward. So if we look at A, if we were to fold it on the dotted line, like these are origami instructions, we fold that over, everything would line up, right? So that is a correct line of symmetry. And we're to circle the figure itself. On this little pentagon here, though, however, if we fold that down, we'd have something like a cockeyed envelope. So that one does not get circled. The heart, if you folded that over, right, the two lobes of the heart would match up perfectly. And on this piece of elbow macaroni, or whatever it is, half a donut, if you were to fold over this, obviously you would not, you could draw a line of symmetry here, right? And same with the pentagon, you could draw a line of symmetry, but that's not it. And now I'm going to switch to my line tool. So we're to find and draw all lines of symmetry, all of them, for the following figures. And then write the number of lines of symmetry that you found in the blank underneath the shape. And we're going to make certain assumptions, of course, like this doesn't say this is a regular trapezoid, that the opposite sides are equal, but it, it looks like it. And it doesn't say that this is a square, that this is an octagon, but we're going to make those assumptions. So with the trapezoid, you can't draw any diagonal. Basically think of lines like as horizontal, vertical, diagonal. There's more to it than that, but that's just a good starting point, what to look for. We can't draw a horizontal line anywhere along this figure, obviously, and fold it over and have everything line up. Diagonals don't work either. If you look and you think, oh, maybe they do, you'd end up with something like a crooked M. So what's the only line of symmetry we have here in this trapezoid? That's right, straight down the middle. So that's our line of symmetry. And then to write how many lines of symmetry, there is just that one there. All right, so let's go to Mr. Square. Hi, Mr. Square. So when we look vertically, can we fold in half vertically right down the middle? You betcha, as somebody used to say. So how about horizontally? Can we fold it horizontally? Yeah, and everything will line up just fine. All right, so we could draw a line of symmetry there. How about on the diagonals? Yeah, you'd end up with two right triangles, right? Eventually you discover the Pythagorean theorem. Oh, that one's shoddy. Shame on me. Do it over. All right, I will. Fine. There we go. That's better. I don't have to be perfect, but gosh, make an effort, man. All right, and the other diagonal, of course, the same is going to be true because a square has 4 equal sides. Are there any more we could draw there? Any more lines of symmetry on the square? So we have the cross and the X. Yep, so how many lines do we draw? 1, 2, and then the X is 3 and 4. So 4 lines of symmetry for a square. We go to friendly, happy little Miss Octagon. Let's try from the vertices here. So from each vertex, of each angle, the point of each angle. So if we were to try one, let's try one out here. Does that work? Yeah, it sure does. And how about from all of the opposite vertices? Yeah, that works. Can we do it through all of them? All of them? Yeah, you can picture that folded over, making yourself a nice taco shell of sorts. Yeah. Tacos, tacos, tacos. Now, is that it? You betcha not, because, right, we can find the midpoint of each side and then draw a line of symmetry to the midpoint of the opposite side. For example, going from the top to the bottom, you could see, right? Oh, yes. So we drew, let's just keep count as we go. 1, 2, 3, 4, which makes sense because there are 8 angles. And now we'll probably, don't you think, be able to draw 4 more through the sides, through the midpoint of each side. You'd be able to fold it there. and here. It's spider web, spider web. Octagon is now a spider web. There we go. Ooh, yeah. That feels good. So we did 4 lines of symmetry connecting opposite vertices and another 4 connecting opposite midpoints of the sides. That's unsurprisingly a total of 8. I wonder if there's some connection when you have a regular figure between the number of sides and the number of lines of symmetry. Nah, it can't be. All right, let's go on. Dang it, now I got the Spider-Man theme song stuck in my head. All right, but lines of symmetry we'll return to. So let's look at our little friend the Pentagon here. Well, I think it's easy to see, as we noticed before when we looked at it, we could draw one straight down the center here. Right? We noticed that earlier when we looked at part 1. So now how about if we were to go from this vertex through the opposite side as well? Could we pass from a vertex through the midpoint of the opposite side, and that would create a line of symmetry? Let's try one. So from this vertex through the midpoint of the opposite side. Does that look like you could fold that over and it would be all lined up? I think so. Gosh, I wonder if we could do that for all of them. Is there another one? Oh yeah, look, I have 2 more vertices here. Yes. And there's one more. You can't believe the degree of concentration it takes for me to do this. So unsurprisingly, you'll find 1, 2, 3, 4, and 5. So 5 lines of symmetry for this regular 5-sided figure. And now we're getting into some irregular figures, to be sure. When we look at this jobby, well, obviously because of the clipped corners here, we can't fold it either horizontally or vertically. Could we do the diagonal though? No, you'd kind of end up with the mountain thing going on. Can you see that? Can you see how this would not fold over to here if we did a line across this end or there? So how many lines of symmetry are there in this little piece of paper with the corners folded down? Yeah, there are 0. There are 0 lines of symmetry. That doesn't work, right? How about through this one? No, because it's a rectangle, it's not going to work. If this were a square with clipped corners, then we'd be talking about something different. Because it's a rectangle, if you were to bisect these 2 short sides, or if you were to draw through the opposite vertices in the other direction, it would almost but not quite be symmetrical. Now this cloud, I believe, is drawn to be as irregular as possible. So like there's no mystical Illuminati secret here, like, aha, you can draw one. No, there's just no lines of symmetry going on there. There are 0 lines of symmetry. Sorry, cloud, we still love you. Now with this arrow though, can you see one right off? That's right, long way down. If you fold in half that way, it will be symmetrical. So we found the, can I move that? Yeah, I can move them. How about, can I fold it horizontally? Right down the middle? Would that fold over and line up? Yes, it would. All right, so I can draw another one here. Are there any diagonals or anything like that I could do as well? No diagonals happen of any sort. Okay, so we just have 2 lines of symmetry there. Pretty good. Good job. Double-ended arrow. Now, how about this jobby here? I'm assuming, I don't know if there's something wrong with my head or my eyes, but I'm assuming that this is not warped. That if we were to draw one straight down the middle here, does it look like that would be symmetrical? I don't know. Maybe my head's not on straight today, but is that a line of symmetry? Basically, right there? Or is this thing kind of a little too irregular? I don't know. I think that's it. I think that is a line of symmetry. If your teacher says otherwise, okay, I'm wrong, and you can, cry me a river. All right, and then on the broken cookie over here, we see a line of symmetry there. Yeah, we could put it right through the midpoint of this arc and the midpoint of the straight side, and that would fold over nicely, but not in any other direction. We can see there's nothing happening anywhere else. So again, here we just have one line of symmetry. Beautiful. We're all done with number 2. Let's go take a gander at number 3. This is probably something you've done for fun and probably in a much more complex way, but we're given half of each figure below has been drawn, and then use the line of symmetry represented by the dash line. So here's one for A and there's one for B to complete each figure. Okay, so when I look at this rectangle, I want to add the other half of the rectangle. And so I have 1, 2, 3, 4 squares by 2 squares. So when I go to draw it, drawing straight lines with this thing's hard. 1, 2, 3, 4. Go over 2 and back up 4. Hallelujah, it doesn't look horrible. All right. Good enough? Right? You've probably done this kind of thing, like, you know, drawing a face or something, folding paper in half. And so now this will is a trapezoid. We have one set of parallel sides and end up being a slightly larger trapezoid. So this top goes over 2. Here's how I'm going to do it. I'm going to complete the top line by going over 2 squares, and then complete this bottom line by going over 1, 2, 3, 4, 5 squares. So 1, 2, 3, 4, 5. And now it's easier to draw the diagonal. If you just go ahead and draw the diagonal, that's a little tricky. It does pass through the vertices of this grid, the intersection points, but not bad for a teacher, huh? Pretty good. Moving on. So on C and D, we have this innocent-looking triangle, and then we have this wackadoodle whatever thing over here. So the way I'm going to do this triangle is I'm going to say, okay, I'm going to find the point, and we're going to end up making it a quadrilateral. We'll call it, I know, a diamond, which isn't really a geometric figure, but hey. 1, 2, 3, 4 squares high. Okay, so if I'm just going to mark that point. 1, 2, 3, 4 squares. And that's the point that it will come to. Now I'm going to grab my line to it, and you might want to use a straight edge unless you're better than me. And I'm going to connect there to there. And then I'm going to connect there to there. See, so I found the point of the triangle before drawing the lines. Hey, that's my best one yet. I feel awesome. Okay, so now I'm going to do a really sloppy one just to make up for that. So this line is, just kidding, I'll try. This line is 3 blocks on the grid. Okay, so 1, 2, 3. And then this one's 1, 2, 3, 4. So I'm going to go up 1, 2, 3, 4. And now this comes over 1, 2, 3, 4. The shorter side. 1, 2, 3, 4. And see, so I'm again leaving that diagonal line for last. And connect this point to this point. Hey, that's not so, it's not so bad. All right, moving on. So number 4, we're giving something of a philosophical quandary here. Is there another shape that has the same number of lines of symmetry as a circle? And then we are to explain. Well, I believe this was covered in class today, right? But if you think about it, okay, when you're drawing lines of symmetry in a circle, if you have a center point, I'll go ahead and best I can locate the center of this circle. If you were to draw a line anywhere, and you don't have to do this on your paper, by the way, I'm just making sure you understand something here. I could draw a line anywhere through the circle as long as it passes through that center point, and that's a line of symmetry. Now if I go and do something that does not pass through that center, that's called a chord, but it is not a line of symmetry. And when you start thinking about it, because remember, right back in lesson 1 when we talked about points, we said that they represent a location on a plane. Points don't actually take up, length and width and height. So it just represents a location. So when you think about it, if you were to ask the question, how many points are there on the circumference of this circle? There's actually an infinite number of points. Now here in reality world, if I were to ask like how many pixels make up the circumference of this circle, that would be an actual number. If I were to ask, you know, what's in centimeters or millimeters or micrometers or even the smallest unit of measurement, it would still be a definite number, a defined number. But it's an undefined number. It's an infinite number because we're talking about points, and geometry exists in the ethereal realm here. So a circle has an infinite number of lines of symmetry. So let's just state that to start our answer. A circle, I was thinking an infinite, a circle has an infinite number of lines of symmetry. Now let's ask ourselves why. Yes, because all points on the circle are the same distance from the center. So because all points, in fact, that's actually the definition of a circle. All points on the circle are the same distance. We could say equidistant, but we'll say the same distance from the center. Now, is that true? Here's the big question. Put on your thinking face. Is that true of any other figure? Think about a square. If you were standing in the corner of a square, as opposed to in, say, the midpoint of one of the sides of the square, that's not the same distance, is it? It's not wildly different, but it's not the same distance. In fact, if you had a say a square drawn, and you took a pencil, and that pencil reached from the center point of the square to the midpoint of the side, and you started rotating that pencil, it would no longer touch the side until you got back to the midpoint of that side, right? So a circle has an infinite number of lines of symmetry because all points on the circle are the same distance from the center. And that, my little friends, is not true of any other shape. There's no other figure where all points on the figure are equidistant from the center. Okay, so this is a tricky question. So yeah, I'm just kind of like laying out a highfalutin answer for you maybe, but I'm hoping you're understanding it. Now notice, as we were doing before with those regular figures, when we got to the octagon, when it's a regular octagon, and if we were to go to a nonagon, a decagon, and on, we would find that there were more and more lines of symmetry. In fact, there's a direct relationship between the number of lines of symmetry and the number of vertices or sides in a regular figure. And so as we had more sides and more vertices, we would have more lines of symmetry to the point where we would begin to approach somewhat infinity. But of course, those would become figures that no one could draw, not even like with a computer. All right, so a circle has an infinite number of lines of symmetry because all points on the circle are the same distance of the center, which, this is a long sentence, I know, is not true of any other shape. Okay, so I realize that, yeah, that's not really so much a fourth grade answer, but I'm hoping you're understanding where I'm coming from with that. I'm trying to make it accessible yet somewhat mathematically correct. All right, well, woo! Wow, I know this homework time started off like pretty lackadaisical. Draw lines, it's wonderful. Now we're getting into like circle philosophy. All right, but I hope you enjoyed tonight's homework time, and I'll see you again next time. It is once again homework time.